Okay, so today we're going to talk about Lesson 6, Area Under a Curve. We've already discussed this a little bit when we talked about definite integrals. We discussed the fact that the whole point of finding a definite integral really is to find the area under a curve between 2 points, A and B. So all of this up here is just telling us that we're looking for the area under a curve between 2 points A and B, and in order to find that area, of finding the definite integral of our function, y equals f of x, between A and B. So let's dive right into some examples here. So example 1 says, find the area of the region enclosed by y equals 2x, the x-axis, x equals 0, and x equals 4, using a geometric argument, and then by using integration. So let's start by taking a look at what this function resembles. So I've already gone ahead and graphed this function in Desmos. You could graph it on your graphing calculator for good practice. But here's the function y equals 2x. You can see that it's a linear function going through the x-axis with a slope, or going through the origin, with a slope of 2. So we've got the function y equals 2x, we've got our x-axis down at the bottom, and we're looking between the vertical lines when x equals 0 and when x equals 4. So we're looking for the area of the curve within this region. Pretty quickly as we look at that, we can see that is a right triangle. And it's a right triangle that has a base length of 4, because we're moving from x equals 0 to x equals 4. How could we find out the height of that right triangle? In other words, what's the value of y, or of our function, when x equals 4? Well, when x equals 4, the value of our function is going to be 8. So our height here is 2 times 4, 8. I can find the area of that triangle pretty easily. Area of a triangle equals times height divided by 2. So I've got 4 times 8 divided by 2, which gives me 16 units squared. We don't know what the units are there. Unit squared is a nice thing to write so we can make sure that we remember that we're talking about area. Remember, our units for area are almost always squared. And so we're looking at 16 units squared. We've done that without using any calculus, any integration whatsoever. Let's take a look from the perspective of integration. So if we're using integral calculus to find the area underneath this curve, what we're really looking for is the definite integral of 2x dx between 0 and 4. So we've got to be able to take the definite integral of 2x. And in order to do this, we need to use our reverse power rule. So remember, our reverse power rule is that if we have the integral of x to the power of n dx, then that's going to be x to the power of n plus 1 over n plus 1. We add 1 to our exponent, and then we divide by that new exponent. So the integral of 2x is going to be 2 times x to the power of 2 over 2. And we're looking to evaluate that between 0 and 4. Some of you may also have recognized that the integral of 2x is just going to be x squared, because when you take the derivative of x squared, you get 2x. So these 2's are going to cancel out, and we end up evaluating x squared between 0 and 4. And you'll remember for definite integrals, what that means is that we replace the x with 4, so I've got 4 squared, minus our lower boundary, which is 0, 0 squared. So I have 16 minus 0, which gives me again 16 units squared. So we've been able to solve this problem using kind of a geometric argument, a bit rudimentary, works well for linear functions, could be a bit more complicated for a function that looks like this. So we're looking for the area of the region enclosed by y equals x squared plus 1, the x-axis, and x equals 1 and x equals 2. So let's think about this. Y equals x squared plus 1. Ignoring the diagram that I've already put in there, you should know that that's going to be a parabolic function, and it's going to have its vertex at y equals 1. So we've got a parabolic function centered on the y-axis with its vertex at y equals 1. So if we take a look there at what that function looks like, here it is. And we're looking for the area of the region enclosed by our function y equals x squared plus 1. Oops. Still getting used to this. There we go. So that's our green function there. And we're looking between x equals 1 and x equals 2. So we're looking for this area right in here. I would recommend drawing a quick diagram of this when things are complicated, just so you can get a visual on it. So we're looking for this area. As you can see, it would be pretty tricky to find the area of this without using integration. We could probably find pretty easily this area. But the rest of it up here is not a perfect triangle because this parabola is actually curving here. So we've got to use calculus or integral calculus in order to solve for this. So what we're looking for is the definite integral of x squared plus 1 dx between x equals 1 and x equals 2. So if we evaluate that, we end up with the integral of x squared is going to be x cubed over 3 plus the integral of 1, which is x, evaluated between 1 and 2. So we end up with 2 cubed over 3 plus 2 minus 1 cubed over 3 plus 1. And I can pretty much hear some of you groaning right now because we are in fact looking at using some fractions here. And this would be a paper 1 question, so you would not be using your own technology to solve this. You'd be doing this by hand. So let's take a look at this. It's really not so bad. We're not going to freak out. So we end up with 2 cubed, that's 8. So I've got 8 over 3 plus 2, which is the same thing as 6 over 3. We know we're going to have to add those eventually, so we're finding those common denominators. And then I've got 1 cubed over 3, well, that's 1/3, plus 1, which is the same thing as 3 over 3. Adding these together, I've got 8 plus 6, 14/3, minus 1 plus 3, 4/3. I end up with 10 over 3 units squared. Remember that you can check your work here using your calculator. And remember that function, you'd graph the function first, y equals x squared plus 1, and then you're going to go to second, trace, and then dy dx. It'll then ask you to put in your upper and lower boundaries, and away you go from there. I'll post a video on how to do that just in case you've forgotten. All right, last example for lesson 6. And our most complicated one, of course. We want to find the area enclosed by one arch of the curve y equals sine 2x in the x-axis. So y equals sine 2x. Let's think about that. What does that graph look like? Y equals sine 2x. We know that y equals sine x goes through the origin, and it moves in an upward direction, and its period is pi. If you remember this value, we called this the b value when we studied sine and cosine functions. Our b value told us about our horizontal stretch. So what we need to do here in order to find the period of sine 2x is divide our period by b. So our new period is going to be, so the period of sine 2x is pi over 2. So if we're looking at the graph of this function, which I'll pull back out here, the area enclosed by one arch of the curve y equals sine 2x, which is what I've graphed right here, and the x-axis, we're looking at this first arch right here. It's going to touch the x-axis again at at x equals pi over 2. So we're really looking for this area under here. So in order to do that, what I need to find is the integral of sine of 2x dx between 0, where that arch starts, and pi over 2, where that arch ends. Finding the integral of sine 2x shouldn't be too bad. We need to use our reverse chain rule there. We know the integral of sine of x is negative cosine x. So the integral of sine 2x is going to be negative 1 over the coefficient of x, which is 2, of cosine 2x. And we're looking to evaluate that between 0 and pi over 2. So let's take a look at that. I have a hunch right now, if we're looking at 0 pi over 2, we're probably going to have to use our unit circle, but let's see first if that's going to be necessary. So the first thing that I like to do here is we can take out our coefficient. We don't have to worry about it too much. And then we're looking at the integral of cosine of 2x evaluated between 0 and pi over 2. So we've got negative 1/2 times cosine of 2 times pi over 2 minus cosine of 2 times 0, which gives me negative 1/2 times cosine of pi minus cosine of 0. As I suspected, we've got cosine of pi, cosine of 0. We've got to think about our unit circle here. We need to find out the value of those functions. Do not default to your calculator here. This would absolutely be a paper 1 question. You need to have your unit circle memorized. So let's take a look at our unit circle. We've got our x and y axis. Over here we've got the point 1, 0. Up here we've got 0, 1. Over here, negative 1 on the x-axis, 0 on the y-axis. And down here, 0, negative 1. We know that this arm represents an angle of 0. Up here, pi over 2, pi, 3 pi over 2, and then back around for a full rotation of 2 pi. We know that our x-coordinates represent the value of cosine, and our y-coordinates represent the value of sine. So if I'm looking for cosine of pi, I'm going to my angle pi, and cosine is going to be represented by my x-coordinate. So cosine of pi is negative 1. Cosine of 0, I'm going to my 0 angle. Cosine is going to be represented by my x-coordinate. Cosine of 0 is going to be positive 1. Some of you may just have that memorized, which is really great. The more you practice this, the more likely you are to be able to memorize it. So I end up with negative 1/2 times cosine of pi, which we said is negative 1, minus cosine of 0, which we said is positive 1. So negative 1/2 times negative 2, which gives me 1 units squared. And that's the area of that first arch of my function y equals sine 2x. Alright guys, let's look at lesson 7, the area between two functions. We can actually find the area that's contained between two curves using integration. And it's not too far off from what we looked at, finding the area between a curve and the x-axis. We're just throwing an extra curve in there. So ignoring, I guess, this blue box to start, let's jump right into an example, and then we can come back here if we need to. So looking at example 1, we need to find the region enclosed by y equals x plus 2, a linear function, and y equals x squared plus x minus 2. And I hope you guys recognize that that is quadratic and therefore a parabolic function. So let's take a look at these types of questions as they all follow the same types of steps. The first step is going to be find the intersection points between your two curves. And I'm really sorry about my messy printing. I think I need an Apple Pencil. So we need to find the intersection points between our two curves. And we know in order to do that, we need to set our two functions equal to each other and then solve for x. So we've got x plus 2 equals x squared plus x minus 2. I'm going to have to retry that one. X plus 2 equals x squared plus x minus 2. So to solve this, we probably want to get everything onto one side and set it equal to 0. So subtracting x and 2 from the left side, we end up with 0 equals x squared. We have a positive x here minus x, which is going to cancel that out. We're subtracting 2 from both sides, so we end up with x squared minus 4. This is a difference of squares, and so factors into x plus 2 onto x minus 2. So our x values of our intersection points are going to be at x equals -2 and x equals +2. So we found our intersection points there. The second step is going to be to figure out which function is on the top and which function is on the bottom. So if we're thinking about these functions, we have a linear function with a y-intercept of 2. So y equals x plus 2 is linear with a y-intercept of 2. And we have a parabolic function or parabola that opens upwards. It's concave up. And it has a y-intercept of -2. I'd be willing to bet that the linear function is on top and that our parabola is the bottom. Just to make sure, it's never a bad idea to graph these. And I've already done that for you. Here's our graph from Desmos. So this is our function y equals x plus 2, our linear function with the slope of 1 and a y-intercept of 2. And then here's our function, the black one, y equals x squared plus x minus 2. And we can see that indeed our linear function is on the top and our parabolic function is on the bottom. And you can see that we have our intersection points at x equals -2 and at x equals +2. So we are right on both of those. We want to find the area between these two curves. So that area is going to be right here, between the top and the bottom. And there you go. So our last step here is that we're going to take the definite integral, but we're going to take it in a slightly different way. So we're going to use our definite integral to find the area between those two curves. So we're looking for the definite integral between -2 and 2, our lower and upper boundaries, which you'll notice are the same as the intersection points. And what we're going to do is we're going to take our top function, x plus 2, and subtract from it our bottom function, x squared plus x minus 2. So we're taking our definite integral between our two intersection points as our boundaries of our top function, subtract our bottom function. The easiest way to do this, in my opinion, is to start by subtracting those functions from each other. So we're still looking minus 3x x 3. X squared plus 2x minus 3 is a quadratic trinomial, and the coefficient on x squared is 1, which means I might be able to use product sum. I'm looking for two numbers that multiply to give me negative 3 and add to give me positive 2. Those two numbers are going to be positive 3 and negative 1, which means that this quadratic trinomial factors into x plus 3 onto x minus 1. If you're unsure of yourself there, it's a good idea just to FOIL that out and make sure that you end up with the original quadratic trinomial. So our solutions here, x-intercepts, or in other words, our intersection points, are going to occur when x equals 0, negative 3, and positive 1. We have 3 x-intercepts. That seems a bit strange. We haven't looked at much like that yet. we have 3 x-intercepts here. We haven't seen that in a while. We really don't look at cubic functions too often. But let's take a look at this one. In order to find out what function is on top, either the x-axis or our cubic function, I think it's probably best just to look at what the graph of this function looks like. So let's take a look at that. I've already graphed it on Desmos for you. And here it is. So here's our cubic function right here. You can see our x-intercepts at 0, or at -3, 0, and 1. Here they are. Here's -3, here's 0, and here's 1. So if I'm looking at finding the area between this curve and the x-axis, I've got this arch right here. Between -3 and 0. And then I've also got this arch down here between 0 and 1. So in this instance, between -3 and 0, my top function is going to be my cubic function. In this instance, between 0 and 1, my top function is going to be my x-axis. And what we're going to find is that when we find the area of our first arch, this area is going to be positive. And this area is going to be negative. The way we're going to combat this is in our third step here, when we use our definite integral, is we're going to do 2 separate definite integrals. And we're going to put them together in a way that's going to eliminate the fact that one is positive and one is negative. Because we want to find the total area. We don't care that that area is underneath the x-axis, that second arch. We want to count that within the total area of the function between the x-axis. So our definite integral is going to look like this. Integral between -3 and 0. So we're looking at the area of the first arch of x cubed. What was our function again? Plus 2x squared minus 3x dx minus the integral between 0 and 1 of the same function. That subtraction is going to cancel out the fact that the area of that section of the curve between the x-axis, between 0 and 1, that second arch, is going to be negative. Because when you subtract a negative from a negative, you end up with a positive. So we can find the area, or the integral then, of x cubed plus 2x squared minus 3x. That's going to give us x to the power of 4 over 4 plus 2x cubed over 3 minus 3x squared over 2. And we're evaluating that between -3 and 0. Subtract the exact same integral, x to the power of 4 over 4 plus 2x cubed over 3 minus 3x squared over 2, and evaluating that between 0 and 1. I'm not going to go through all of those with you, but when you plug 0 in here for your upper boundary, you end up with 0. Plugging -3 in for our lower boundary gives us 0 subtract -45 over 4, subtract -7 over 12, which is our value when we plug in 1 for x, minus 0. So I end up with positive 45 over 4 plus 7 over 12. To get a common denominator, we're going to make that 45, multiply it by 3 to get 135 over 12 plus 7 over 12, which gives us 142 over 12 units squared. an equivalent answer, which would be just as good, would be 71 over 6 units squared. But remember there that IB does not require you to simplify your fractions.